How quantum computing and AI are converging to reshape tech careers. Your job title today will mean something completely different in 3 years. Tech professionals across data science, machine learning, and systems architecture are discovering that their current skill sets cover only half of what employers now expect. Today, quantum computing and AI are merging into hybrid systems. The convergence creates entirely new professional categories, while fundamentally altering existing technical roles. Let's cover which specific technical competencies are evolving right now. Why quantum computing and AI convergence create new technical skill requirements. Quantum AI systems demand fundamentally different expertise than classical computing or traditional AI/ML roles. Professionals need cross-domain fluency in quantum mechanics, linear algebra, and machine learning architectures simultaneously. Quantum algorithm design for machine learning applications. Think about how long it takes classical computers to solve complex optimization problems. Days? Weeks? Quantum algorithms solve these AI problems exponentially faster. This involves translating machine learning tasks into quantum circuits that process information in superposition states. Understanding quantum gate operations and their AI optimization uses quantum gates to manipulate qubits to perform computations. These gates optimize neural network training and feature extraction in ways classical bits never could. Each gate operation creates transformation possibilities that fundamentally change what's computable. Hybrid classical quantum system architecture systems now combine classical computers for preprocessing with quantum processors for complex optimization. The two communicate through specialized interfaces. Which tasks go to quantum hardware? Which stays classical? That decision alone requires deep technical judgment. Quantum error correction in AI training environments. Quantum systems experience errors from environmental noise. This is a major problem. Error correction codes protect quantum information during AI model training. This maintains quantum advantage by enabling longer computational sequences. Otherwise, the whole thing falls apart. How hybrid quantum AI systems transform existing tech roles. Because of this shift, data scientists, ML engineers, and systems architects are adding quantum capabilities to their skill sets, rather than switching careers entirely. Data scientists adding quantum feature engineering. Quantum algorithms extract features that identify patterns classical methods miss entirely. Quantum feature spaces reveal correlations hidden in high-dimensional data. Data scientists determine which features benefit from quantum processing, since not everything requires quantum treatment. ML engineers implementing quantum-enhanced model training. Quantum processors integrate into model training pipelines. Quantum circuits accelerate specific optimization steps in gradient descent. ML engineers determine when quantum acceleration actually provides real performance gains versus classical approaches. Sometimes, classical still wins. Cloud architects designing quantum classical infrastructure. Cloud systems now seamlessly connect quantum processing units with classical infrastructure. This includes managing quantum resource allocation, job scheduling, and result validation. Cost considerations balance between quantum and classical computing resources. As of now, quantum time remains expensive. Research scientists bridging theoretical and applied quantum ML. Someone has to translate theoretical quantum computing research into practical AI applications. That someone identifies which quantum algorithms solve actual business problems. Academic breakthroughs mean nothing without commercial implementation. Why traditional programming paradigms become insufficient. Remember learning to code. Variables, loops, conditionals, functions, clean, sequential, deterministic. Forget all that. Quantum computing fundamentally changes problem-solving approaches in AI. Deterministic, sequential thinking from classical programming requires complete relearning for quantum systems. The mental models that got professionals this far actually become obstacles. Quantum computers work with probabilities instead of definite outcomes. Algorithms accept probabilistic results while delivering reliable answers. How? Quantum circuits run multiple times to build statistical confidence in results. It feels weird at first. Superposition lets qubits explore multiple solutions simultaneously. Entanglement creates correlations between qubits that classical bits cannot replicate. These quantum properties solve optimization problems that would take classical computers centuries to solve. Quantum circuits replace sequential code. Each circuit represents specific computations through gate arrangements. The thinking shifts from step-by-step instructions to quantum state transformations, which is a completely different mindset. How organizations are restructuring teams around quantum AI capabilities. Today, companies are building dedicated quantum AI teams and embedding quantum specialists within existing AI departments. These structural changes create fresh career paths that did not exist 2 years ago. They now have quantum AI research labs in traditional tech companies, cross-functional teams combining quantum physicists and ML engineers, consulting roles bridging business strategy and quantum AI implementation, educational positions teaching quantum computing to AI professionals. Why early career positioning in quantum AI offers strategic advantages. A timing opportunity exists right now to establish expertise before market saturation. The field remains young enough that becoming a recognized specialist happens quickly. Think about cloud computing in 2010. Early positioning creates long-term career advantages that compound over decades. Few professionals currently possess quantum AI skills. This drives significantly higher salaries than traditional AI roles. Premium compensation results from companies competing for a limited supply of quantum AI talent. Supply and demand are working exactly as expected. The growing interest in emerging technologies also extends beyond careers. Many professionals are exploring quantum AI investment stock opportunities as commercial applications of this technology continue to develop. Financial markets follow technical innovation. Common misconceptions about quantum AI career transitions. False assumptions prevent qualified professionals from pursuing quantum AI opportunities. Let's clear these things up. Believing quantum physics PhDs are required for entry-level positions. You don't need a doctorate in quantum physics to start. Many roles require only foundational knowledge of quantum computing, combined with strong AI skills. Quantum fundamentals can be learned through online courses and self-study. Assuming quantum computing will replace rather than augment AI wrong. Quantum computers enhance specific AI tasks, not replace classical systems entirely. Quantum processing handles specific optimization problems, while classical computers handle most other work. Hybrid approaches combine both computational paradigms. Waiting for production-ready quantum systems before learning. Current quantum systems already prove useful for research and development. Valuable experience comes from working with today's quantum hardware. Waiting for perfect quantum computers means missing years of learning opportunities. The time to learn is always now. Thinking career transitions require complete role changes. Current roles expand rather than face abandonment. Data scientists add quantum feature engineering to existing toolkits. ML engineers incorporate quantum algorithms into familiar workflows. Building on current expertise is always preferred over starting everything from scratch.